Welcome back, everyone. So, if you're gearing up for university exams or, those brutal technical whiteboard interviews, getting a rock-solid grip on function parameters in C++ is absolutely crucial. Seriously, it's a make-or-break topic. Today, we're doing a full explainer of Lecture 32 by Skip Uni to master exactly that. We're going to dive right into call by value in C++ and call by reference in C++. Then we'll put them head-to-head to finally settle the pass-by-value versus pass-by-reference debate. And to top it all off, we're going to completely demystify how pointers and references in C++ actually work under the hood. Let's get into it.
Okay, here's our roadmap for today. We'll start with passing parameters, look at actual versus formal, tackle call by value, move on to call by reference, see how using pointers fits in, and wrap the whole shebang up with a syntax review.
All right, Section 1, Passing Parameters in C++. Moving right along, Section 2, Actual versus Formal Parameters.
So the fundamental problem we're trying to solve here is basically communication. How do we send our precious data from the main program into totally separate, isolated functions? Well, knowing the players on the field is step one. First up, we have actual parameters, which you'll also hear called arguments. Think of these as the original, real-deal data living safely in your main program. Like in the example we're about to look at, we'll have local variables named A and B that are created the second the program's compilation starts in main. These are the actual tangible pieces of data you want to work with.
Now, on the flip side, we've got formal parameters. These are your receiving variables. Think of them as empty containers declared inside the function definition. Let's say a function named test. When that function gets called, these formal parameters are essentially standing out on the field, gloves ready, waiting to catch the data being thrown to them from the main program. It's really interesting when you put these two side by side. It's your real data versus the receiving container. Actual parameters, they live in main. Formal parameters, they live in the function definition. You definitely want to lock this distinction in your mind, because honestly, mixing these two up is a super common trap on university exams. Don't fall for it.
Okay, Section 3, Call by value. I want you to think of call by value exactly like making a photocopy of a highly classified document. You hand someone the photocopy, they can scribble all over it, spill coffee on it, whatever, but your original document remains perfectly safe and clean in your filing cabinet. To see how this plays out, let's look at a starting memory map. We've got an integer a holding the value 3, sitting pretty at memory address 100. And we have integer b holding the value 4, hanging out at memory address 200. These are our actual parameters, right? They each have their own totally distinct spaces in memory.
Now watch what happens when we pass b into our test function using call by value. The system actually creates a completely separate memory location for the formal parameter, which we'll just call y. Let's pretend it's at address 300. The system then simply copies the value 4 from b and pastes it right into y. So now we literally have two completely separate 4s living in two completely separate memory locations.
Here is the absolutely crucial point. Because these are isolated memory locations, any changes made to y inside the function, well, they stay in the function. If our function takes y and multiplies it by 2, y becomes 8 over at address 300. But what about b back in the main program? It absolutely does nothing to it, zero impact. Variable b at address 200 safely remains 4. So when your control flow jumps back to main and you print b, it's just going to output 4. Now, that photocopy method is incredibly safe, no doubt. But it kind of begs a massive question, doesn't it? What if we actually want to modify the original data from inside the function? What if we want to save memory and avoid making those clunky copies altogether? Well, that brings us to Section 4, Call by Reference. If call by value was a photocopy, call by reference is like collaborating on a live shared Google Doc. Everyone is editing the exact same page at the exact same time. The magic secret to this in C++ is the ampersand symbol in the formal parameter, like $x. When the system sees this, it does not create a new memory block. It doesn't go hunting for address 300 or 400. Instead, it simply creates a nickname, or an alias, x, that points directly to our original address 100 where a lives. Basically, x is a and a is x. Let's see how this builds out in our memory map. We pass a into the function, and it gets aliased as x. Inside the function, we write x equals x plus 5. Now, because x is literally just a direct reference to address 100, we take the original 3, add 5, and it becomes 8. You are directly updating address 100. So when that function wraps up and we return to main, printing a will actually output 8. We did it! We successfully changed the original data.
All right, moving on to section 5, using pointers and memory.
Now, using explicit pointers is a little bit more manual. Instead of that seamless shared document, you treat memory addresses like literal GPS coordinates and navigate there yourself. Here's the step-by-step. Step 1, down in your main program, you don't pass the variable A. No, you pass its specific memory address, which in our little example is 100. Step 2, your function has to catch this address using a pointer variable. You denote this with an asterisk, like int *x. And step 3, to actually read or change the data at that coordinate, you must use the dereference operator. Let's look a little closer at that dereferencing step because it's super important. When you type *x equals *x plus 5, you are essentially telling the computer, hey, go to the exact address stored in x, which is 100, grab the value sitting there, which is 3, add 5 to it, and shove that new value, 8, right back into address 100. Just like the standard reference we looked at a second ago, pointer dereferencing alters A directly to 8. And meanwhile, remember our call by value variable B? Yep, still totally untouched, sitting safely at 4.
Okay, let's bring it all together. Section 6, syntax comparison and review.
You know, getting the concepts is really only half the battle. Being able to write it flawlessly on a whiteboard while an interviewer is staring at you, that's the other half. Visualizing the difference between the ampersand alias and the explicit asterisk pointer is absolutely key. The lecture actually strictly advises students to drill this distinction into their heads. The ampersand means, hey, I am an alias for an existing variable. The asterisk means, I am a special variable that holds a memory address. Seriously, mixing these two up is probably the most common compilation error beginners face in C++. So let's quickly review our core takeaways from the source material. Call by value safely copies the data to a brand new address. Use this when you absolutely positively don't want your original data touched. Call by reference, using the ampersand, seamlessly aliases the data, making your syntax nice and clean. And call by pointer passes the literal memory address and requires manual dereferencing, which gives you that absolute low-level control C++ is famous for.
Which leaves us with this final, kind of provocative thought. We know call by value copies data, right? And sure, copying a tiny little integer is lightning fast. But think bigger. What if you're dealing with massive, megabyte-sized data structures? If call by reference completely avoids making memory copies, could using it make your C++ code significantly faster and way more memory efficient? Keep that burning question in mind as you move into advanced programming, because that is exactly where the true, raw power of C++ lies. Thanks so much for joining me on this explainer, and hey, happy coding!